Greetings, geometry students. This is a re-recording of the truth tables lesson. Apparently the one that was posted on Edmodo developed some sort of an audio problem, but at any rate, here it is again. Title for today is Truth Tables. Our objective for this day is the student will apply logical reasoning to truth tables. Now, truth tables is probably something that might be totally new to you, unless you have maybe messed around with it in some science experiments and things like that. So we're going to be going over it in pretty good detail. I'm going to have you doing this. The student will demonstrate the ability to construct and read truth tables from provided scenarios. And your essential question for the day is, can I connect the logic of truth tables to the reasoning skills that we have discussed? As always, anytime you need more time to copy something down, just press the pause button and then hit play when you're ready to move forward. Okay, so we spent a little bit of time here recently looking at reasoning and conjectures and negations. Along the way, while we were talking about the various conjectures and their negations, we talked a good bit about the truth of those statements, and we found that sometimes when you take a good solid conjecture, a truthful statement, and start changing it in various ways, that sometimes a truthful statement becomes completely untrue, or maybe only partially true, and sometimes remains entirely true. It just depends upon the statement. Another way to demonstrate visually what's going on with those truths is what's called a truth table. Okay, so here's a definition. A truth table displays the absolute truth of the parts of a statement and then weighs the truth of the statement as a whole. Now, as you probably are well aware, mathematics deals in absolute truths. And what you're going to see as you go higher and higher into the mathematics is that we can evaluate the truth of complicated statements by looking at the truth of each of its parts. As you go higher and higher in math, you'll find out that the rules that we come across sound more complicated, but mostly it's because more and more qualifications have to be met in order for the rule to actually apply. So truth tables is very much the way that we look at those type of rules in mathematics. We kind of weigh the truth of each of the individual parts of the rule in order to decide if the rule has truth or not. Okay, so let's begin by looking at some basic vocabulary and symbols that we're going to run into with truth tables. Okay, a typical word that we run into is the word not. Now, not can be displayed graphically using what's known as a tilde, a little squiggle, kind of like the guy that we've seen over the top of our congruent symbol in Unit 1. Now, when you see either one of these guys, it means inverse. And if you remember, what an inverse did is it took part of our conjecture and it negated the meaning. Meaning things that used to be true became false, things that used to be false became true. It simply reversed the meaning of the verb. We're also going to run into the word and comes in some symbolic notations. First off, this guy is called a caret in mathematics, a little rooftop looking guy. Okay, but he means and when we're talking about logic statements. And there's another symbol that we bump into from time to time. It looks like an upside down capital U. And all three of these guys, anytime you run into any of them, basically their translation is it means that all parts of a statement must be true in order for the statement to be true. Another term that we run into is the term or. And you'll see the same two symbols that we just discussed a moment ago, yet they have been rotated 180 degrees. So now instead of both of them having their vertex, so to speak, on the top side of the symbol, now it's been turned around and it's on the bottom side. All three of these guys, when you see them, basically they mean any part of the statement being true means the whole statement is true. And another guy that we run into is this arrow. And when you run into him, he means truth in part of the statement leads to another part of the statement. In other words, you kind of have to meet one qualification before you even worry about any other qualifications that might be coming along in the statement. Okay? So let's start off with a statement P, and we're going to compare it to its inverse, not P. Okay, now you may remember the P and Q notation from our conditional statements that we talked about. It could be any variable, not necessarily just P and Q. It's just a placeholder. So some statement P, and we're going to compare it to its inverse. Okay, so this is what a P not P truth table would look like. Okay. Now there's only two entries that show up in truth tables, and those entries are true and false. Okay, so let's say we start off with a true statement. Okay, so whatever statement it is, whatever piece of information we have, it is a true statement. And if you remember from discussing inverses, inverses reverse the meaning of the statement. Okay, so if your original statement is true, then not P is going to be false. It is the inverse. Okay, and on the flip side of that, we could always start off with a false statement. And if you took a false statement and then looked at not P, its inverse, it would go from being false back to being true. Okay, now that's not anything really new that we're talking about there. We're just kind of getting you started on the truth table idea. We should have already known that that's what an inverse would do. We're just demonstrating it graphically in a truth table. So we should have already known that that relationship was already existing. Okay, but you can see how the truth table is going to demonstrate truth and non-truth. Now the tables get bigger as we do different things with them, so let's take a look at some of that. Okay, typically with a truth table, we are dealing with two pieces of information, kind of like we've been dealing with two pieces of information on our conditional statements. One thing has to happen, and then another thing happens as a result or simultaneously, just depends on the situation. Okay, so let's take two statements, P and Q, and we're going to examine what is called an AND table. Okay, now here's what an AND table would look like. Okay, so we have a column for whatever information P is, we have a column for whatever information Q is, and then we have the AND part of that. P and Q must happen at the same time. Now it's actually going to take 4 rows of information, because if you think about truths and falses, when you fill them in, there's 4 different combinations of true and false that can exist between P and Q. For example, we could start off with both pieces of information being true. And if you have a good P and a good Q, and they are both true, then that is going to lead you to a true AND statement. Because as you remember from the couple of slides ago, we said that AND means both things have to happen in order for the final statement to be true. Okay. Now, let's look at the 2 rows in the middle here, and those would exist where perhaps we have one piece of information that is true, but one piece of information that is false. As we have already said, in order for an AND truth table to be entirely true, then we need both pieces of information to be true. So the AND statement, P and Q, would yield a false statement. And then the only remaining combination of true and false would be both statements being false. And if both statements are in fact false, again, that is going to lead us to a false AND statement, because as we said, both pieces of information have to be true in order for the AND statement to be true. Okay, so in order to be true, an and statement must be built entirely out of true statements. And this can be expanded. Okay, right now we're looking at two pieces of information, P and Q, but honestly it could have been 100 pieces of information, but all 100 of them would have had to have been true for the and statement to be true. If even one of them was false, then the entire and statement would end up being false. Okay, now still using P and Q, let's take a look at an OR table. Okay, so once again, we have a column for P, we have a column for Q, and now we have a column for P or Q. Okay, once again, 4 rows because there are 4 different combinations of what P and Q might do with each other as far as truth and false. Okay, so again, we'll start off with both P and Q being factual pieces of information, so both statements are true. That is going to lead you to a true OR statement. Just like before, now let's look at one of the situation where one or the other is actually a false statement, but the other one is true. And as we already said, in order for a true OR statement, all we need is any one piece of good information in the statement, and we end up with truthful OR statements. So in those cases, the OR statements are both true. And then the last situation would be both statements being false. And if that happens, then your OR statement is absolutely going to be false because there is no truth to any of the information that is going into the OR statement. Okay, so in order to be true, an OR statement needs only any true statement within it. Okay. All right, now P and Q, we're going to look at what is called an implication table, or sometimes called a conditional table. Okay, and this comes out very much the same. You see we have the little arrow for implication. Okay, and that basically means one thing must happen before the second one really even comes into play. That's how come it's also called a conditional table, meaning it's got conditions attached to it. Okay, but let's start off with the situation where P is a truthful statement. Now that needed to happen before Q even becomes a consideration. So if P is true, then that leads to the information about Q. Okay, now also, after P leads us to Q, now we end up with a Q that is also truthful after looking at it. And what that's going to give us to is an implication or a conditional statement that is also true. So P was true, that opened the possibility of Q, then we looked at Q and decided it was true as well, and then we end up with a truthful implication table. Okay, now let's look at the possibility that P is true once more, and that does lead us to Q. But then when we look at Q, we find Q to be false information. Okay, now if that's the case, then what we have is a false implication or conditional statement, meaning one thing happened that was supposed to happen, and that led us to a second thing that ultimately let us down, and that led to a false statement. Now the final two combinations of true and false there would deal with the P statement being a false statement. Okay, so we'll start off with P being false. Now if P is false, then that basically puts us in a spot where it does not really matter what happens to Q. So Q is actually no longer important because the thing that had to happen in order for the implication table to work didn't happen in the first place. So ultimately the statement is truthful. It's not its fault that the thing didn't work out. Okay, the condition that had to apply in order for the statement to have a chance didn't happen in the first place, so we actually consider the statement itself to be truthful. So that's how come the implication column on the right there both got trues for the false P's. Okay, so let's look at some examples here real quick. Let's consider the statement, if grass is fed and it is watered, then it grows. Okay, this is an and table. You can read the vocabulary right there in the middle of the sentence. If grass is fed and it is watered, so two things had to happen in order for this to work. Okay, so the first situation is if you have truth in your P and your Q, then you have truth in your and statement. Food and water for the grass equals growth. Okay, this time let's assume we have truth for P and then false for Q, and that would lead to a false statement in an and table. If you have food for your grass but no water for your grass, then it is not going to grow. And if we reverse those truth and false there, again, now this time P is false, but Q is true. And in the and table, that still leads us to a false statement. That basically said, if you water your grass but don't feed it, then there will be no growth. And of course, you can guess what the final line is going to say if we have both false statements for the grass being fed and it being watered. Obviously, it is not going to grow at all. Okay, so there's kind of how an and table would actually apply to a real situation. Okay, let's look at an example for an or table. If I make money or find some, then I am happy. Okay, so here's the or table. Okay, so we started off with both P and Q being truthful statements and said the or statement would be true as well. So basically, that is I've made money and I found money, so I am obviously happy as a result of that statement. If we allow Q to be false, that would basically mean I made money, but I did not find any money, but I still made money, so I am happy. Okay, reversing the truth and false of that previous statement, that would be I found money but not made money, but I am still happy. With the or statement, only one or the other has to happen. And then, of course, if neither happen in the end, then we are not happy. No money made or found, we're not happy. Okay, so that's an example of how an or table might apply in a real situation. Okay, now let's look at the one that really kind of needs to be considered, and that would be the implication or the conditional table. If I make an A in geometry, my mom gives me $20. Okay, now you can see the difference between this statement and the two previous statements. In order for this one to work, something must happen first. Okay, so here comes the implication table. Implication table is true all the way across for starters, and that would be I make the A, I get my $20. The statement is a good statement. Now the next line suggested that if the first condition did happen, but the second one did not, that would yield a false statement. So let's look at it. So you do your job and you make the A, and then mom goes back on her word and does not give you your $20. Obviously that breaks the statement down. You did what you were supposed to do, then something did not happen as a result of it that was supposed to happen. So obviously the original statement is a lie if this happens this way. Now these last two lines were the ones that kind of are the eyebrow raisers right there, and it's basically if the problem starts off with a false. Okay, well here is why the statement is true even if the statement starts off with a false. Okay, the entire statement is based upon the if, that is the hypothesis, the thing that must happen in order for the conclusion to make any sense. But if we don't live up to the hypothesis and you don't make your A, then whether mom was going to give you the $20 or not doesn't even come into play. So the statement really doesn't have an opportunity ever to become false because we never did what we should have done to get it into motion in the first place. So that is how come the statement on the implication for that is considered to be true. You didn't make the A, so the $20 does not come into play. The statement was, or at least had the possibility of being true. It just wasn't given the chance to develop the way it should have. Okay, that's the basics on truth tables. We're going to be going very deep into logic and logical reasoning and things like that in this unit. So this is a kind of a next logical step in the progression. So I appreciate you finding time to get your notes taken care of. Those of you who had to wait for me to re-record the video, I apologize. Should be posted here in a couple of minutes.